Okay, we are now moving on to probability, which is chapter 2 for statistics year 2. This does come up in year 1, so this is the year 2 content, which now includes conditional probability. So what I want to start off by talking about is I strongly advise you watching the applied year 1 chapter 5 probability summary video first, as I will not be covering Venn shading and notation. That's already been learned about in applied year 1. I won't be covering independent and mutually exclusive events, and I won't be covering tree diagrams. These things will come up in the video, but I won't be teaching sort of like how to do them. I'll just be going straight in and actually using them. So the thing that we're going to be looking at is this stuff to do with conditional probability. It's kind of the theme of this whole chapter. And so I'll tell you a bit about conditional probability over here. So often the probability of one event occurring can change depending on if another event has occurred or not. So this thing that we've got over here, this PA line B, this is the probability that A is going to happen, given that B has already happened. And the way you find this, there is a version of this formula in the formula book. It's got this probability of B is kind of multiplied up here, and I think the letters are the other way around, but it's quite easy to remember this formula because the numerator is the probability that they both occur, and the denominator is the probability of the second letter that we have there. And we can sometimes speed this up rather than using this formula by using something called a restricted sample space. Again, this is going to be something that I will do in one of the questions, and it will make a lot more sense when we kind of have a look at that part that we've got. And then last of all, if events are independent, then the probability that A happens, given that B has happened, is the same as the probability of A. And if we just kind of talk about the logic of this, even though it is in the formula book, it's saying that if A and B are independent, it doesn't matter whether B has happened or not. A will still have the same probability. So if the probability that A happens, given that B happens, is just the same of the probability of A happening, well, it doesn't matter then if B happened or not. In other words, they are independent from each other. They don't have that kind of conditional relationship between them. So you'll often find Venn diagrams can look quite complex in year 2. So this time we've got, it says 3 events, which is a terrible sign of Mr. Bison not being able to even count. But this obviously shows the 4 events, A, B, C, and D. I'll change that in the PDF, and their associated probabilities where P, Q, R, and S are constants. And they could also ask you some stuff about mutually exclusive events. If you were to pick a pair of mutually exclusive events, you could pick A and C because they don't overlap, C and D because they don't overlap, or A and D because they don't overlap. But if you picked anything with B, obviously B is related to all of them because it's got some overlap with A, C, and D there. But it didn't ask us that. That's something that maybe it could do though. The first thing it says is given that the probability of not B or B complement is 0.47, find the value of P. Well, the value of not B is everything that is outside B like this. So this is telling us that Q plus R plus S is equal to 0.47, which isn't particularly useful because we're trying to find out what P is equal to. Well, I guess we could do this, right? If I know from the first place, if the probability of B not occurring is 0.47, then that tells us something about the probability that B occurs. That would be 1 minus 0.47, which is 0.53. So sometimes the information in the question, you might want to kind of play around with it. So this means that the probability of B, all of this stuff here, is 0.53. So that's great. We can now say that P plus 0.18 plus 0.3 plus 0.03 is 0.53. It's a very simple equation to just solve what P is equal to. Now 0.53 minus 0.18 minus 0.3 minus 0.03, and we get that P is 0.02. Now something I often find very useful to do with this is to just go to your diagram and then add in that we now know that P is 0.02. So it says here for part B of the question, given further that the probability of B given D is 0.3, and that the probability of A is 0.15, the probability of B union D not, find the values of Q, R, and S. So there's quite a lot of stuff going on in this question. I think we're going to just take these things one at a time. So I'm going to look at this probability that B given D is 0.3. I'm going to talk to you about the formula after I show you the restricted sample space. So it says given that D has happened, that means we are only looking at this yellow part that we've got here. We're imagining that the entire Venn diagram has disappeared and the only thing we have left now is this part because we're restricting the whole sample space down to this information that D is the only thing that has happened, or D is the only part that's left. So if I was going to look at that restricted sample space, I would say, what is the probability of B happening out of this whole section? Well, the probability of B given D would just be 0.03 for B, and out of the probability of that whole space, it would usually be 1, wouldn't it? But it's not going to be 1 in this case, it's going to be R plus 0.03. So that's from the restricted sample space. If I was going to do it from the formula, we would have, remember, the top part is the probability of B and D occurring, and the bottom part is the probability of the second letter, which is D. And then if we look at this on our diagram, the probability of B and D is 0.03, and the probability of D is R plus 0.03. And so actually we've ended up with the exact same thing. This was the restricted sample space. It's just a visual way of kind of thinking about this that we've got here. So they've told me that this thing on the left-hand side, the probability of B given D is 0.3. So I can now say that 0.3 is equal to 0.03 divided by R plus 0.03. So I'm actually going to multiply up. So I get 0.3 multiplied by R plus 0.03 is equal to 0.03. You're welcome to expand the brackets if you want to. My brain wants to do this. I want to do 0.03 divided by 0.3. So I can now calculate what R is by doing 0.03 divided by 0.3. There's so many zeros and threes in this. And I'll divide them, and then I'm going to subtract 0.03 so that I get R is 0.07. Let's add it to the diagram so we can get more information about what is going on here. And we're going to continue. It now says the probability of A. So I'm going to just box this part off so it doesn't look like it's getting confused with it. The probability of A is 0.15, the probability of B union D complement. So the probability of A is Q plus P, which is Q plus 0.02. We're then going to have 0.15 multiplied by, well, you can do shading with pencil and always kind of rub it out in the exam. B union D, this is B or D, this is B union D. So B union D not is everything that has not been shaded, which is Q plus S. So we've got now this equation, and it's a combination of Q and S in one single equation. So that's 0.15 Q plus 0.15 S. I'll get it all onto, I'll come back to that, okay? I might need to do something with that in a second. Now, there's one other fact that I haven't used, which we always use in these probability questions. We know that the sum of all the probabilities must be 1, okay? So all of these probabilities that we've got here have to add up to 1. So I'm going to now say, using the sum of the probabilities being 1, what's that going to be? We're going to have Q. I'm going to add up all the numbers on my calculator to save a bit of time. So it's 0.02, 0.03, 0.07, 0.18, and 0.3, that is 0.6. So Q plus 0.6 plus S, which is on the outside, is equal to 1. So we get Q plus S equals 0.4. So what I need to do, I've got a pair of equations now. I'm going to solve these simultaneously. So I'm going to get this one into a form that looks like this. So if I do Q, take away 0.15 Q, I get 0.85 Q. If I subtract the 0.15 S, I'll put the 0.02 onto the right-hand side so that I get this, which means I'm now going to solve this equation and this equation simultaneously, and I can just put that on my calculator straight away. So my coefficients are 0.85 and minus 0.15. That gives me minus 0.02, and then I have 1, 1, and 0.4. And we get some quite nice looking answers, which makes us feel like we've done it correct, but it wouldn't be a problem if we got fractions. We got that Q is 0.04 and S is 0.36. So we have now got our values for P, Q, R, and S. I am going to add this onto the diagram though. So we get 0.04 and 0.36. And then for part C of the question, it says find, and then we've got to do another kind of interesting Venn diagram. We have the probability of C or not B and D. Well, this is quite easy because when you do union, you just shade one of them and then shade the other part and we just add them together. So this is the C part that we've got here. And then I'm going to do also, I'll probably do it in the same color. I'll do this not B and D. So it has to be inside D and it has to be not inside B. Well, that part is inside B. So it is just going to be this part that we've got here in union, you just take both parts of those together. So it's going to be the 0.3 plus 0.07. So this is for part C of the question. We've got the probability of C or not B and D is 0.3 plus 0.07 that we have there. Okay, now our last part is to determine if A and B are independent. If you want to, you could do the year 1 technique for this, but I'm probably just going to do the new technique, which is this one that we've got written down here like this. So I guess I just need to find out the probability of A and then the probability of A given B and just do a comparison. So the probability of A is 0.04 plus 0.02, which is 0.06. Let's come up here to give me some more space. And I'm also going to compare it with the probability of A given B. So the probability of A given B, well, the probability of B, I think we know from earlier on, is 0.53. So we're looking at this restricted sample space of 0.53. And we're saying, well, how much of that is going to be A that we've got there? So that's going to be A is 0.02. That's the probability of A and B out of the probability of B, which is 0.53. Pretty obviously, this is not going to be the same as 0.06. This is 0.0377. So I can say the probability of A is not equal to the probability of A given B. Hence, A and B aren't independent. Okay. So all this time I'm using the highlighter. You might find doing it with like pencil in the exam is a good way of going about it. We're going to now do some stuff using some probability formulae. So we're going to keep using this one that we've got here. And we may also be using this one that's also in the formula book. I'm just going to very quickly explain how it works. So the probability of A union B is the probability of A plus the probability of B. But because this part we've just shaded twice, we need to subtract that A union B so that we don't have it overlapping, so that we only have it kind of being shaded once rather than being shaded twice. And my exam tip here is that drawing a Venn diagram can be a very useful starting point because just using the formulae, I think, can be pretty abstract. So here we have Shumi and Tom both play for an esports team. The events S and T are defined as follows. S is the event that Shumi wins her match, and T is the event that Tom wins his match. We've got the probability of Shumi winning, the probability of Tom winning, and the probability of Shumi or Tom winning as 0.4. And we're going to find the probability that it's not Shumi, given that it's not Tim. In other words, what's the probability that Shumi loses, given that Tom loses? So I am going to draw a Venn diagram, and that might help us kind of visualize what's about to go on in this question. So we're going to have the S and the T. And I don't think we can do an awful lot of filling in just yet. So I'm probably going to do this part with the formula, okay? I'm going to say the probability of S, U, T. That's the probability of S plus the probability of T minus the probability of S and T. And I'm also going to show you how you can do this without the formula as well. So that's 0.4 is equal to 0.25 plus 0.3 minus the probability of S and T. So doing a bit of rearranging, the probability of S and T is going to be 0.25 plus 0.3 minus 0.4, which is 0.15. So now on the Venn diagram, I can say that the overlap in the middle is 0.15. And the probability of S is 0.25, so that must be a 0.1 that goes in here, so they add up to 0.25. And this must also be a 0.15 for the probability of T. Now, I'm going to show you how you could have done this without the formula booklet, without the formula that we have there. I'll do it really, really quick, okay? I know that the probability of S or T is 0.4, so this whole thing that we've got here is 0.4. And I know that this part, for example, is 0.3. So if this whole thing is 0.4 and the T loop is 0.3, then this part outside here must be 0.1. I could have done that logic the other way around. I could have said that the whole thing is 0.4. The S loop is 0.25, which means this part over here must be 0.15. And we can then obviously reason that the middle part is 0.15. So using it as like a visual tool, you can avoid the formula entirely. And then this must mean that the outside area is 1 minus 0.1 minus 0.15 minus 0.15, which is 0.6. I could have done that even quicker because I knew this whole section was 0.4, so the outside must be 0.6. So now I've got the Venn diagram, I can actually go straight in and answer the question. I'm going to find the probability that Shumi loses given that Tom loses. This is probably, you can do the restricted sample space if you want to. The probability that Tom loses is this area that's on the outside. So we know that it's going to be out of 0.7. And the probability that Shumi loses, well, Shumi loses on the outside is going to be 0.6 out of 0.7, which is 6/7 that we've got there. Now, if you wanted to do it with the formula, you would do the probability that it is not S and not T over the probability that it is not T, and you come up with exactly the same thing that we've got here. Okay, the probability of not S and not T is this 0.6, and the probability it's not T is those things. So our next part of the question is to explain why S and T are not statistically independent. Now, again, you could use year one techniques for this if you wanted to, but we've already done this calculation. Okay, we've calculated the probability that not S is going to occur given that not T has happened. Well, I can just compare that to the probability that it's not S. Although we did the definition here with A and B, if you had not A, you could just replace A with not A. If you wanted to replace B with not B, any of those things can be replaced as long as you're still talking about the same event. So the probability that it is not S is clearly going to be 0.75, either from here or from these two things. So the probability that it is not S is 0.75. The probability that it's not S, given that it's not T, is 6/7. So the probability is of not S is not equal to the probability of not S given that it's not T. Hence, S and T are not, I'm not going to write that word, I can't be bothered, are not independent. You could have done it with S and T. You can also do it with not S and not T. That's perfectly acceptable here. Now, this second one, this exam tip of drawing a Venn diagram is going to be very, very helpful because trying to use the formula with this is possible, but I think it's a lot more challenging. I do actually think just a Venn diagram is such a perfect tool to help us think about what's going on. So let's begin. I'm going to have A and B, and they've told us the probability of A and B is 0.05. And they've told us the probability of not B is 0.3, and they've given us a bit of a clue here to encourage us to think about, well, let's find out what the probability of B is. The probability of B, if not B is 0.3, is 0.7. So I think this is now going to help us work out some of these other things that we've got. We've got the probability of B is now 0.7, which means this probability over here is 0.65. And then I want to try and use this information. Now, if you do it with the formula, you get something a lot more complicated. You're going to end up with the probability of not A or B, which is 0.7, is the probability of not A plus the probability of B minus the probability of not A and B. It's possible, but it's just a bit more tricky to do, okay? I'm going to show you how you can do it just with the Venn diagram. So let's look at this. The probability of not A or B. Well, not A is going to be everything that is outside A. Or B means we can also include this 0.05. So you can now say to ourselves that this area, and the outside area is 0.87. So that's this area plus this area plus the outside area, let's just call that X, is 0.87. So we get 0.87 minus 0.05 minus 0.65, which is 0.17. So I now know that the outside area is 0.17, which means I can find out what this last remaining area is. So I will do 1 minus 0.17 minus 0.65 minus 0.05, which gives me this part as 0.13. And so I can say that the probability of A is equal to 0.13 plus 0.05, which is 0.18. Let me see if I could do this with the formula. Okay, let's see if I can do it with the formula up top. So we get 0.87. Now the probability of not A would have been this 0.65 and some unknown, which is X. The probability of B we have got as 0.7, and we'd be having to subtract the probability that it is not A and B. Well, the thing that is B and also not A is 0.65, so we would be subtracting a 0.65. The 0.65s cancel, and we just do 0.87 minus 0.7, and we still get the same thing as X is equal to 0.17. So this is using the formula, but again, I still think I needed this Venn diagram to help visualize what was going on here. I'll just get rid of that X so that we can see that it's been replaced with the 0.17. And it says to draw a Venn diagram to represent events A and B. I've already done that, so it's perfectly fine. Do make sure when you do your Venn diagram that you draw the box on the outside. If you don't draw the box on the outside, you usually get deducted a mark for that. And then my last section is using tree diagrams, because using tree diagrams can be useful, but sometimes it can be more confusing. This is one where I probably would do a tree diagram, but I would be very, very careful about what needs to be filled in, because it can be an awful amount of time to get this done. Now, the difference with this tree diagram is that our probabilities are conditional, and you'll hear that throughout this question, why it's conditional. So the probability that Jerry is late for school on Monday is 0.2. If Jerry was late to school one day, the probability she is late the next day is 0.3. So it's like if she was late one day, she's even more likely to be late the next day. If Jerry was not late to school one day, the probability she is late the next day is 0.15. So if she was on time one day, she's even more likely to be on time the next day because her probability of being late has decreased. And we're going to calculate the probability that Jerry is late exactly one day out of Monday, Tuesday, and Wednesday 1 week. So she could be late on Monday and then not late on Tuesday and Wednesday. She could be not late on Monday, late on Tuesday, and then she could not be late on Wednesday. She could be not late, and then she could finally be late on Wednesday. Now, if you try and go straight in with the probabilities, it is absolutely possible to do that, but I think you might enjoy using a tree diagram for this, but I'm not going to do a full tree diagram. I'm not going to draw all of the probabilities necessarily, okay? Now, I'm going to use colours for this. In an exam, you could do it with like a blue pen and a black pen, or you could do it with like a pencil and a pen, something that just kind of draws a distinction between these. So it says here, I'm not going to worry about this first sentence, but it says if Jerry was late to school one day, the probability she is late the next day is 0.3. So if she starts off being late, we're going to have a probability tree that looks like this, where it's going to be 0.3 for late, and it would then be 0.7 for not late. So we get that kind of pattern. If she is not late on one of the days, we're going to get a slightly different coloured tree that we have. The probability she is late the next day is 0.15, which means not late would be 0.85. And so I'm going to try and draw what this tree would look like. Now, Monday is just going to be a different colour because we actually don't know what happened the day before Monday. Well, it was a Sunday, so I guess she wasn't going to school. So she was either late or not late. Now, if it's a red late, there's going to be red branches because that's the different probabilities that we have from this section. So she's either going to be late or not late. That's for the Tuesday. Now, out of that late, there's going to be another of these red ones where it's late or not late. Out of the not late, there's going to be the green branches. There's going to be late or not late. Now, for the bottom section, we've now done the Monday, Tuesday, and Wednesday if she was late on Monday. If she's not late, we're going to have these two options. Again, I should be replicating this tree that we've got up here. There's going to be late or not late. If she was late, we'll draw this red tree that we've got. And if she was not late, there's going to be this green tree that we've got where she's either late or not late. Now, I know this looks complicated, but the main thing that we've noticed is that if she was late on one day, we've got this red bit that's going to be replicated. If she's late, we've got another red bit. If it's green, we've got a green bit. If it's green, we have green. If it's red, we have red. If it's green, we have green. Pretty confusing this, okay? And we're going to have all these different probabilities that go with it. Now, I'm not going to fill in all of the numbers. I'm going to just start off by looking at these ones that we have over here and decide which branches I need to use. So I want to have the late, not late, not late. That's one of the routes that I want to use. The other route I'm going to want to use is not late, then not late. And my final one is going to be not late, and then late as the last part. So filling in these probabilities that I'm going to need to know about, we've said that anywhere there's red, it's 0.3 and 0.7. I mean, I can fill them in if I want to, but that's a bit of a waste of time filling them in at the top, isn't it? And over here, I'm going to need them. That's a 0.3 and a 0.7. And then for the green ones that we've got, we've said it's 0.15 and 0.85. So that's 0.15 and 0.85, 0.15 and 0.85, 0.15, 0.85. And I'm going to just do this for the sake of completing it. Oh no, I've actually have completed it. There's no other bits that are needed. Apart from, we don't have these probabilities. This is the Monday. Late on Monday is 0.2, which means that not late is 0.8. Now you could try and do this just from here, okay? You could just go and do these probabilities just from here. In fact, I'm going to grab these, if I can, and put them down here because I'm going to be using them right now. So this first one that we have, late, not late, not late, is this pathway here. It's going to be a 0.2, a 0.7, and a 0.85. Now, you could have done this without the tree, right? That's being late on Monday, and then not late when she was late the day before would be 1 minus this, and then not late when she was not late the day before would be 1 minus this. Now, our second one that we've got is not late. So we're doing this branch, this branch, this branch. Let's get those numbers written down first. That's 0.8, 0.15, and 0.7. Again, you could have come up with these without drawing the tree diagram, but it might be a bit tricky of thinking about them. So that's not late. Given that she was not late, being late the next day is lower than being on time the next day is even lower than it was here. I'm not going to do that explaining on the last one because hopefully by now you've got it. And our last part is this two and this one. So that is 0.8, 0.85, and 0.15. So the probability of late on one day is just going to be the sum of all of these things added together. Sum them up. So it's 0.2 times 0.7 times 0.85 plus 0.8 times 0.15 times 0.7 plus 0.8 times 0.85 times 0.15, and we get 0.305. So you wouldn't get necessarily any marks for doing this. This is where all the marks would be, okay? The tree diagram can be a visual tool for this. I don't know whether this is entirely necessary. I like it for this sort of teaching video to kind of give you a bit of an idea of what I mean by it. It might be a bit too confusing. You might like to try and do it like this, but it's so easy to slip up and select a wrong number for this. You'd have to be very, very careful with how you do this. So probability is going to pop up in other areas. It's not always going to be questions like this. Probability is obviously a lot more of an idea in statistics, where it can be applied in other things to do with binomial distribution, normal distribution, which comes up later in probability year 2, in statistics year 2 as well. So that was everything for this chapter, and I hope to see you in another video soon.